Okay, so today we're talking about Chapter 4, Section 1, Anti-Differentiation. Okay, so anti-differentiation, that is a mouthful. However, we're just gonna, we'll interchange anti-differentiation and integration. However, for the most part, it is called integration, but the concept of it is uh, the opposite of differentiation, which is why we call it anti-differentiation. Okay. Starting off in the first paragraph, in this chapter we explore integration, which is one of the two principal branches of calculus, which we have, and we of course we've done differentiation through the first three chapters. With integral calculus, we are able to determine accumulation of quantity based on a given rate function. For example, if we have some function y is equal to v of t, which is the velocity of an object at time t, we can determine an object's distance traveled over an interval of time by integrating. Given a function, the marginal profit of a business after X units have been sold, we can determine the business's total profit after X units have been sold by integrating. And of course, the last function, again, we integrate and we can find a function. And at the end of this section, we will do a couple of word problems and actually see how integrating does actually work, and how we can determine new functions for just any given, um, well, I won't say word problem, but any given real world theme. All right, so what is the process of integrating? Well, starting over here to the left, right here. All right, so it reads, one aspect of integral calculus is anti-differentiation, which is a process of differentiation in reverse. All right, so we have some function. Let's jump down here right here. All right, so the function capital F is going to be denoted as the antiderivative of lowercase f, okay, or the integral of it. So for example, if we have some f of x equal to 2x, then if we integrated it, we would do the opposite of differentiation, and we would get capital F of x equal to x squared. Okay, so whenever we differentiated, if you recall, what we did was, and let's just look at this function here. We would take the exponent, put it out in front of the variable, and then reduce the exponent by 1, right? So the derivative of x squared is 2x, while the antiderivative, or the integral of 2x, is x squared. Again, it's just doing the exact opposite. So instead of well, we take the 2 that's in front, and then we put it on the x. Okay, or um, more realistically, we'll see that we actually, we do indeed take the x, the 1, we turn it into a 2, and then we divide by 2, right? When we took the derivative, we multiplied by the exponent. When we integrate, we're going to divide. Of course, division is always a pain. Okay. All right. So next up, note the functions like capital F of x equals to x squared plus 5 and capital F of x equals x squared minus 17 are also antiderivatives of 2x. Okay, so that makes sense because, well, if I asked you to take the derivative of this particular function, okay, well, you would say, okay, well, never mind the 5. We don't care about the 5. The derivative of x squared is 2x. True. Well, it's the same thing here, right? We don't care about the 17. All right, the derivative of x squared is 2x. Okay, so it doesn't really matter what the constant is, okay? But we do kind of run into a little bit of a problem, because it appears that if we take the antiderivative of some function, the constant seems to, it doesn't really matter what the constant is. Right? It just seems to pop in the way. Right? And of course, we see that in Theorem 1. So the antiderivative of f of x is a set of functions, capital F of x plus c. Okay. Now, this plus c, I remember taking calculus, and I remember all my classmates. I'm telling you, every single one of us would always forget the c. And I bet many of you might also forget to put the c as well whenever you take the antiderivative, or the integral of a function. Okay, another definition here. So whenever we have the plus c, okay, when we don't know what the c is, all right, we call that the indefinite integral. Okay, because it's not, well, it's not definite what the actual function is. We just know around about what the function could be, but we don't know what the function actually is because we don't have the information needed to get to that c. Okay, so let's look at a couple of examples. Alrighty, so again, if we were to take, oh, by the way, I guess I forgot to mention this, but the symbol here um, is obviously the integration symbol, right? Whenever this symbol is in front of our function, that tells us that we have to integrate. And of course, that dx tells us, okay, well, we're looking at the derivative here. Okay, so looking at, let me get situated. Looking at a, there we go. We have we're looking for, or we're looking at rather, the integral of 8 and then dx, right, the derivative of such. So in order to integrate this, well, we're going to have to uh, add a variable here. Okay, so if we were to add a variable, then we would end up with just simply 8x. Okay, and real quick, let's just go ahead and derive this in our head. It's pretty easy, right? Now, what is the derivative of 8x? Well, that's going to be 8. So we're good to go. It was a pretty simple problem, okay? But again, don't forget to put the plus c, plus some constant. We don't know what the constant is, but just some constant, or plus some constant. Okay, b, we've got the integral of 3x squared dx. Okay, well, what we're going to do is we're going to take this 3, okay, and well, no, not necessarily. Sorry. We're going to take this 2, and we're going to go up 1. Okay? We're going to go up 1 to a 3. And then we're going to divide the entire problem by 3. So, by doing such, right, that x squared turns into an x cubed. Okay? And then this 3 that we have here, we divide the constant by 3. And of course, 3 over 3 is just 1. Okay? So we have x cubed plus c. Okay, and of course, if we were to again check this, well, we take this 3 down here, we have 3x, and then that 3 turns into 2, so we have 3x squared, which is the exact same. Okay. So again, just doing the exact opposite operation here. Okay. All right, we'll see, if you recall, the derivative of e to the x was e to the x. So conveniently, that's also going to be our antiderivative. Okay. So e to the x dx, that's going to be just simply e to the x plus some constant. Okay, and again, that makes sense because, well, if I were to take this function and take the derivative, well, again, e to the x is indeed e to the x, which we have here. D. D gets a little tricky because we're going to have to recall a function here in a minute. Okay, dx, and of course, provided that x is not equal to 0. Okay, so where have we seen the derivative of something being 1 to the x? Okay, well, we remember that was the natural log. Okay, so this is going to be simply just the natural log of x, and then again, plus c. Okay, and of course, working this backwards, we know that the derivative of the natural log of x was 1 over x. Okay, or indeed, or depending on what the x was, it was 1 over that argument. Okay. All right, so more rules for anti-derivative. I won't say necessarily more rules, but definitely more concise rules. Okay, so up until this point, we're just kind of shown how taking the antiderivative is indeed just doing the exact opposite of taking the derivative. Now we're going to have hard and fast rules to actually work by. Right? So looking at this first one, all right, a1, we're looking at the integral of k, where k is just some constant, dx. All right. So all we're doing there is just simply adding an x, and that's the same thing that we did for a here. Okay, we have the constant, and we're just going to put the variable there. The power rule. Now this is uh, honestly, this is about 80% of the antiderivatives here is the power rule, and it's basically what we just did. All right, and of course we can let's actually look at this down here. This is, I feel like this. I mean, it says the same thing that A2 does, but we kind of see the process here. So we take the exponent, okay? Again, this is step one. We take the exponent and we increase it by 1. Okay? And then step 2, we're going to divide the term by the new power. So whatever the new power is, we're dividing by that. Of course, again, like I said, we saw it here. All right, we took this 2, turned it into a 3. And then take that 3 and divided it by the entire problem, and 3 over 3 was, as we've seen, was 1, or x cubed. Okay. The natural logarithm rule, of course, we did this example a moment ago, right? If we see 1 over x dx, well, that's just going to be a natural log of x plus some constant. And then the exponential rule, we, again, did this as well. If we have e to the, this was e to the example we did was just simply e to the 1x, right? Because that's an implied 1 in front of the x. All right. Well, the derivative of that is going to be just e to the ax divided by whatever that a is. And in our example here, our a happened to be 1, so we just divide the entire problem by 1. Okay, so these are the rules for anti-differentiation. These are rules that you have to, well, I wouldn't necessarily memorize, because again, the concept is the exact opposite of what we have done, right, of differentiation. But, I mean, it does kind of help to understand, like, the algorithm of it. All right, so let's go to example 2. All right, so we're going to crank up the difficulty just a little bit. All right, nice. We got some nice fractions and square roots and stuff here. So looking at A, we're looking at the integration of x to the 7th dx. Okay. Well, what I'm going to do is I'm going to take this 7 and I'm going to turn it into an 8. Okay, so I'm going to turn it into an 8. And then I'm going to divide my my problem by my new exponent. So I'm going to take this and divide it by 8. And then, of course, plus c. Plus c. Okay. Now, the textbook does do this a tad differently. And I'm just gonna note this for this first example, and then I'm gonna do it, you know, I wouldn't say necessarily my way, but to me a more precise and prettier way. So looking at the solution to A, just okay. So notice how the textbook, I take the exponent and divide the entire problem by the 8. Right. Well, the textbook, and again, there's nothing wrong with it. It's just, to me, it doesn't look as good on the eyes as what I have written in the blue. What it does is it takes the exponent and then basically, you know, multiplies it by 1 over that number. And again, there's nothing wrong with it. What the textbook has and what I have, they're the exact same, but I just prefer to write what's in the blue because it looks better. Alright, so B, we have the integral, and let's just go ahead and change the square root of x into something that we know, and we know that we can rewrite this as x to the 1/2, okay, because we need to, we're concerned about these exponents. 1/2 dx. Okay. So what I'm going to do is I'm going to take x to the 1/2, I'm going to go up 1, all right, so instead of x to the 1/2, we're going to have x to the 3/2. x to the 3 halves. All right, and then I'm going to divide it. I'm going to divide this entire problem by my exponent. Well, my exponent is not nice and neat. It's a 3 halves. So unfortunately, what I'm going to do is I'm going to write this as 3 halves in the denominator. Okay, but we're going to clean this up, and let's actually go ahead and clean this up. Going up here, we'll just put C on the next page. Okay. Well, I know that x to the 3 halves divided by 3 halves, right? I know that that's going to end up being 2 x to the 3 halves all over 3. Okay. And then from here, I know that this x to the 3 halves is essentially, it's essentially going to be the square root of x cubed, which I can change that into the square root of x squared times x. And then I know that the square root of x squared is x, so I can essentially make this x on the square root of x. Okay, so I'm going to go ahead and do that. So we're going to have 2x on the square root of x over 3 plus c. Okay. So I won't say necessarily that was confusing, but there was a lot involved there. So I'm going to go over that one more time. Right. So I mean, obviously I didn't put plus c's here because I knew I had to do I had to do more arithmetic. But just to recap here, I took my exponent and I went up 1, right? So 1 half, and I go up 5. If I go up 1, I go up 2 over 2, I get to 3 halves. Okay? And then I take that 3 halves and divide the entire fraction by that. Well, I know that, let me move this toolbar so I can maybe work out and show you the fraction part. Okay, so I know that I had x to the 3 halves, and it was divided by 3 halves, right? That's essentially what this is, right? Well, I know that what I can do from here is I can essentially say, okay, well, that is the same thing as saying times the reciprocal of 3 halves, which is 2/3. And that's how I got the 2 in my numerator and the 3 in my denominator. Right? And from there, we talked about my x to the 3 halves right here. That's the same thing as saying the square root of x cubed. And then as I wrote in the yellow, I can break down x cubed into x squared times x, and I know the square root of x squared is x, and so I'll pull it out like that. Okay, so that was pretty busy. There's a lot going on there. Hopefully we explained it. All right, that's just going to stay. All right, so let's continue with example 2 and look at C. All right, so again, fractions. Nobody likes fractions, but it's part of the process. So C, we're just going to go ahead and rewrite this with my variable in my numerator. Okay, so it's going to be the integral of x to the negative 3 power. So what I have to do, again, is I have to take that negative 3, I need to go up 1. All right, well, what is negative 3 plus 1? It's going to be negative 2. So it's going to be x to the negative 2 power, and then I'm going to divide this entire problem by negative 2. And then, yeah, we'll forego the plus c for right now. Okay, so that's equal to, I'm going to take my x to the negative 2 and put that back in my denominator. So I'm going to have a negative, and this negative comes from, well, let's actually do it this way. We'll keep that negative in the denominator for now. Okay. So in the past, I've said, if you have a negative in your numerator or your denominator, it just looks better on the eyeballs if you take that negative and put it out front. And we're going to do that real quickly. Okay, so we're going to put the negative out front. So we're going to have a 1 over 2x squared, and then we're going to put the plus c. Okay. And of course we have our our antiderivative of the of x to the negative 3. All right, so those are pretty good examples. All right, so we're going to go back and we're going to now look at the exponential. Of course, let's go back and look at our rule one more time before we begin this. So wait for that to move. There we go. All right, so what is our rule for exponentials? Okay, with the base e. Well, if we're taking the integral of e raised to the a times x dx. Well, the integral of that is going to be 1 over a times e to the ax. So it looks like we're just going to be putting the problem over whatever the value of a is. Okay, and a is the constant in front of our x. So let's go look at our problem here. All right, so look, that's in the way. I'm going to take that down. Alrighty. So we've got the integral of e to the 4x dx. Okay. So the a in our example here is going to be this 4. So we're basically just going to put this all over 4. Right? So this is going to be e to the 4x over 4 plus c. And that's it. And again, I'm going to go ahead and snip what the textbook has because they like to put this in a fractional form out front. And again, I say it, I mean, there really is nothing wrong with it. It's just, I don't know. I have my preferences. And honestly, it depends on the textbook because the textbooks that I've grown up with have done it the way I wrote it in the blue, whereas this textbook does it this way. All right, so next up we're looking at some more properties, and again, these properties, they're not, they shouldn't be new to you. Obviously, you know, antiderivatives are new to you, but the premise of them, the whole idea behind this, we've seen this with differentiation. Okay, so what do I mean by that? Well, looking at theorem 3, all right, property 1, if we have the integral of some constant times a function, dx, then we can take that constant and put it out front, and then take the integral of f of x. And of course, we've seen that before, right? If we've seen, you know, something like well, it's not the best example, but something like 3, and we actually do this, but obviously this isn't the step we would do. But if we had 3x squared, okay, well, we learned before that that's the same thing. If we want to take the derivative of it, we put the 3 out front. Let's put this to this dx. Right? We know we put the 3 out front, and then we take the derivative of the variable and work like this. And of course, the derivative of x squared is 2x, and then the 2 multiplies by 3, and we get 6. Okay, so we don't do it this way technically. Well, no, I'll take it back. Technically, we do it this way. We just don't write it down like this. Right? So that's essentially what we're doing here. Okay, if we have some constant, we can take that constant here and put it out front. Just worry about integrating the variable and then introduce the constant back in. Of course, that's what I'm talking about here. I do remember talking about it. I just know that we don't actually go that roundabout way and do it. We just simply multiply the 3 by 2. Okay, and then another concept, again, that should be pretty familiar to you, right? So if we're taking the integral of some function plus some other function, you know, dx, well, then we can split those functions up. Okay, and again, we've seen this, right? If we had, you know, 3x squared plus 2x, right? If we wanted to take the derivative here, we don't have to do any sort of first times derivative of second, whatever, load, we don't have to do any of that. We just simply take the derivative of the first term and then take the derivative of the second term. And that's what we're doing here. We're taking the integral of the first term and then taking the integral of the second term. Okay? Just dividing them up. So let's look at examples concerning this theorem. Okay? So looking at these two problems, they look absolutely disgusting, don't they? Okay, but again, we can just break them down. Of course, this is probably going to be a two-pager, so let's go ahead and just take care of that real fast. All right. All right, so looking at A, we have again we have this function and it's got three terms. It's got three terms in it. And the thing is again, like we don't necessarily have to concern ourselves with the whole problem at once. We can kind of split this up into three individual integrals. So I'm going to go ahead and rewrite this as three integrals. I'm going to take the integral of the first one, 3x to the fifth. All right. And then, I guess for notation's sake, we'll put plus dx, or dx. And then we're going to take the integral of the second one, so 7x squared dx. And then we're going to take the integral of the third one, which is 8 dx. And now we essentially just split this up into three really easy problems. Okay, so let's go ahead and do this. So let's go ahead and take this 5 and turn it into a 6. So this is going to turn into an 8. I'm sorry, not 8. An x to the 6th. And then we're going to divide the entire problem by 6. So this 3 is going to be 3 over 6, or in other words, 1/2. Okay, so it's going to be, 1/2. But of course, that 1 right there is redundant. And then we're going to do plus. We're going to turn this 2 into a 3. So we're going to have x cubed over, and then over 7 divided by 3, so divided by 7/3. And of course, if we were to fix this up, we can take this denominator 3, put it in the numerator there. Again, it's because of, and I'll show you again one more time. Okay. All right. So what I'm doing here, and again, this is what we did on the previous problem before, and I just kind of I wouldn't say I necessarily took a shortcut, but it's just whenever you do fractions a lot, it's you just kind of used to it. But let's just go ahead and look at 7 divided by no, let's not do that. Let's go ahead and do it like this: x cubed divided by and 3, 7. Okay, I actually didn't have to go through all that. I'm sorry. Sorry about that. I got a little caught up in wanting to make things difficult, and I didn't have to. Okay, so real recap. I'm sorry, my brain just floated away. I was trying to make things more difficult than they are. I just take the exponent, went up to 3, and then divide the entire problem by 3. And for some reason I put a fraction down there because again, I just want to make things harder on myself. But that was it. Okay, and then lastly here we have the integral of 8. Well, all we have to do there is just simply put an x. Okay, and then we're going to put plus c. Now really quickly, and I don't know if our theorem discussed this. Not really. All right. Okay, so it didn't really discuss it there. It kind of discussed it here. Okay, so but when we have a problem like this, okay, when I took the integral of each one of these, okay, I said we did them separately. Well, it kind of does make sense. It kind of does make sense to say, okay, well, we're going to have, the antiderivative of 3x to the fifth is x to the sixth divided by 2. And then we could think of it as plus c. And then we could put a plus c here, and then we put a plus c here. Okay, so while technically we could put plus c at the end of every one of them, okay, well, but the thing is if we have plus c attach every one of them, it doesn't really matter what c is. We know that it's just going to be some sort of constant. So we can consolidate all three of those constants together and make it to just to one single constant. Okay, so that's why I didn't put plus c on the end of each one of those, because again, you know, if we're adding constants, then that's all it really needs to be said. We just added constants. I think that about does it. All right, so let's look at b. Now b, again, it's fractions. Nobody likes fractions, but we can simplify this. Right? We can simplify this to make it a little bit easier. And so how can we simplify it? We're going to have the integral of, we're going to put the x in the denominator here under every single one of these, right? We know we could do that. We can split this up into a fraction of every one of these. So we're going to have a 4 over x plus 3x over x, and then plus 2x to the fourth over x dx. Okay. So again, we just split this up into fractions, and then we're going to integrate these fractions one at a time. Okay, but before we do, let's just go ahead and simplify this. Well, 4 over x stays as 4 over x. Okay. The 3x over x, well, we can reduce that into just simply a 3. So plus 3 here. And then the 2x to the fourth over x, well, this x goes away, and this x turns to a 3. So we have 2x cubed at the end. So plus 2x cubed. Alrighty. So now this is going to be our function that we're going to differentiate. Okay. Well, looking at 4 over x, we could, we can go through the process of taking that exponent in the numerator, all that good stuff. But we know that the derivative of the natural log of x is 1 over x, right? So we can essentially write this as 4 natural log of x. Okay, and then if we integrate, let's put dx over here, be consistent. If we integrate that 3, well, that's pretty easy. So plus 3x, and then plus, we take this 3, turn it to a 4, and then divide the entire problem by 4. So we're going to again have a 1/2 x to the fourth. So x to the fourth over 2. That's the same thing as 1/2 x to the fourth, and of course again plus some c, so plus some constant. All right, so this turned out to not be so bad. The fractions, which we can just reduce them, and of course the first example there, a, we just split them up. Okay, and that is I mean that is integration. That's the gist of integration. Obviously things, as always, typically get a little bit harder, but we now have the tools to work on integration problems in the future. But before we conclude, let's look at some word problems here, and we're going to talk about initial conditions. So initial conditions, well, we use initial conditions quite often, especially when we get to differential equations. And this is just a little precursor of what I want to say complicated, how much more complex math can get. Okay, so on this particular course, we've learned a lot of new things. Now we're going to learn even more new things. All right, things that aren't typically taught in your high school curriculum. So looking at initial conditions, reading up here. When a point that is a solution of an antiderivative is given, it is possible to solve for c. Okay, so up until now, one moment. Alrighty, so up until now, our c, well, they've just been c's. There's some constant. We don't know what they are, right? But now we're going to actually solve for those c's. Okay, but we need information to solve for those c's. The first 4 examples, we had no information. We were just integrating our brains out. Now we're going to actually have some information. Okay, this information is going to be called initial condition. So looking at example 5, it reads, find the integral of 2x plus 3 dx given that capital F of 1 is equal to negative 2. Okay, so we are told capital F of 1. So again, the capital F is going to be the integral of our function. Okay, so what we need to do is we need to find the integral. And again, I'm using integral and antidifferentiation or antiderivative interchangeably because they are. But anyways, looking at the problem, let's just go ahead and write this. We're going to go ahead and write this. We don't have to actually write it out right now. I mean, it's written here, and we can integrate this in our head, right? So what is the integral of 2x plus 3? Well, what's the integral of 2x? Well, that x to the first power goes to 2, and then divide the whole thing by 2. So we're going to have x squared. So let's go ahead and denote this as capital F of x, because this is going to be the integral here. Is going to be equal to, what did I say, x squared, and then plus, well, that 3, it gets its own variable, plus 3x, right? And then don't forget the plus c, right? So now this is our function. Okay, we integrated 2x plus 3, and we got our function you see here. Now, our initial condition is that f of 1 is equal to negative 2. Okay, so what that means is whenever I plug in a 1 for x, the entire problem is equal to negative 2. So the way I'm going to write that is I'm going to say, okay, so the entire problem, and that's what f of x is, all right, on the left side here, all right, we're going to put a negative 2 right there, and then we're going to put a 1 in for x everywhere. So we're going to put a 1 here, 1 squared, plus 3 times 1 plus c, and of course you can see how we're going to solve for c here, right? Because it's the only unknown. We're just going to basically put it all by itself. All right, well, 1 squared is 1, 3 times 1 is 3, 3 plus 1 is 4, and then we subtract 4 from both sides. We end up with a negative 6 is equal to c. Okay, so we now have what c is equal to. So my function, my actual function with no unknown, is going to be basically this, except now I know what c is. So it's going to be x squared plus 3x, and then c was a negative 6, so we could say plus a negative 6, or just simply minus 6. So that is the function given that initial condition of f of 1 is equal to negative 2. Okay. So let's do some more initial condition problems, but before we do, this paragraph is very important. Right? I've kind of I think I'm pretty sure I alluded to it earlier in the course. But so the antiderivative of a function has many applications. So for example, in section 1.8, we saw that the derivative of a distance function is velocity. Yeah, definitely covered it. So real quickly, let's go ahead and write this. So we're going to put well, yeah, we'll just put d for distance. Okay, so we're going to put d for distance. We're going to put v for velocity. We're going to put a for acceleration. Okay, so let's go ahead and follow along with the paragraph again. So therefore, if we are given a velocity function, its antiderivative is a function that describes the moving object's distance from a starting point. So if the distance traveled after some time t is known, then we can find a distance traveled over other intervals of time. So in the red, we'll do red. So whenever we take derivatives, okay, so if we take the derivative of the distance, we get the velocity. When we take the derivative of the velocity, we get the acceleration. Okay. Well, obviously, since this is the very simple flow chart we have, the opposite will be true. Okay. So let's see. Let's do. I want to do some notation here. So let's go ahead and put d dx, and it's usually time, but we're just going to put dx for right now. D dx. All right. So if we take the derivatives, we get distance, we get velocity. The derivative of velocity, we get acceleration. Well, the opposite will be true. Okay, so if we take the integral, all right, if we integrate the acceleration, so we'll just put the integration symbol there, we get velocity. And if we take the integral of velocity, we get distance. Okay, so again, we see that the antiderivative or the integral is indeed the exact opposite of differentiation, and we're going to see more of that in the next example. All right, so we have our nice handy dandy physics problem. Okay, so example 6 reads, A rock thrown upwards with the initial velocity, okay, so that, keep that in mind, initial velocity, 50 feet per second from 10 feet above the ground, okay, so 10 feet above the ground, keep those in mind. It has a velocity modeled by v of t, so v of t, keep in mind that's velocity, where t is the number of seconds after the rock is released, and v of t is the feet per second. So we're told a lot of information here, so let's just go ahead and cover them real fast. Sorry. So whenever we throw the rock up, the initial velocity is 50 feet per second. Okay, so keep that in mind. We're going to be 10 feet above the ground, so that would obviously be our height, right? We're going to be 10 feet above the ground. We have our velocity function, and then the variable in our velocity function there is t. So that's going to be t is going to be number of seconds the rock is released, and v of t, or in this, or just simply v, but v of t, v is going to be the velocity in feet per second. Okay, so A is wanting to know determine a distance function h as a function of t. So as a function of time. So we're going to determine a distance function h. So my function's name is going to be h. Okay, and then we're going to make it as a function of time t. Well, luckily for us, our velocity function is already using the variable t, so we're good there. But real quick, let's go ahead and go back to what we have here. And this kind of bothering me, so let's go ahead and center it. Okay, so we have been given a velocity function. Okay, but we're wanting to get the distance function. So naturally, what we have to do is we have to take the integral of the velocity function. Okay, so if we want to kind of work backwards and formulate that distance function, we have to take the velocity function and integrate it. Okay, so if we're wanting to integrate this function, honestly, let's just go ahead and do it the long way, because that's not one of those things I feel like many of you have. Since it's new to you, it's not something I should probably skip and do in my head. So we have our integral of negative 32t plus 50, okay, and dx, because that is, well, actually, I'm sorry, it's dt. The function, the variable here is t. So if we take the integral here, all right, so again, we take the integral, this 1 turns into a 2, and then we're going to divide that entire problem by 2, so we're going to have a negative 16t squared, so negative 16t squared, plus, well, this doesn't even have a variable on it, so we're going to attach one to it, so plus 50t. Okay, we're not done though, because again, we have to put the plus c. All right, let's actually move this over, because the whole point of getting the derivative here is I now know that this is going to be my function h, and then of course of what? Of t. That's the variable being used. So h of t is equal to negative 16t squared plus 50t plus some constant c. All right. Well, we're trying to figure out, the actual function. We have to figure out everything about it, and the only hard part left is to figure out what in the world this c is. Okay. Well, we were given that information. Okay. That information was from a height of 10 feet above the ground. Okay. It was initially thrown 10 feet above the ground. Initially thrown, right? And so what we're talking about is when time was equal to 0, right? We're skipping over the velocity here, mainly because, well, we're not just skipping it for fun, but looking at this function here, h of t, looking at this blue function here, okay? The only variables involved here are h, okay, which is the height, and t, which is the time, okay? There is no velocity in this function. So that's why we're not even messing with velocity to figure out what c is, okay? Because we have the initial time, which is going to be 0, and then my feet, or my height was 10 feet. So what I'm going to do is I'm going to plug in, I'm going to put a 10 for my height, okay? And then I'm going to put a 0 everywhere for t. Okay, and of course this is super duper simple. We can do this in our head. We can do this in our sleep, right? Especially when we multiply by 0. So doing this, we end up with 10 is equal to c. Okay, again, because you know, that goes to 0, that goes to 0, and it's just 10 is equal to c. So let's go ahead and write this on the next page real quick. So it's going to be, all right, so we have h of t, I think it was negative 16 t squared, I think it was a 50 and plus 50t, 50t, and then plus 10. Okay, so we got that 10 because we just solved using our initial condition. So now we now have our function. We've done part A here. We determined, where are we at? We determined a distance function. That's what we have at the top of the next page. And then B, find the height and velocity of the rock after 3 seconds. Well, B is pretty darn simple. Let's go ahead and denote B here. And let's just go ahead and do the easiest one. Well, I mean, actually, at this point, they're both easy, but it wants us to find the height and velocity of the rock after 3 seconds. Well, we already have the velocity function right here. All we have to do is plug this 3 in for t in our velocity function, and we have the velocity. And then, of course, plug the 3 into our height function, and we'll have the height. So my velocity function, 3 times negative 32, it's 96. Negative 96, negative 96 plus 50 is a negative 46. So let's go ahead and be thorough, though, and let's write this out. So my v of 3 was equal to a negative, it was negative 32. Was it negative 32? Yeah, negative 32 times 3 plus 50. Right, and we said that that was a negative 46. Right, and then my h of 3, right, because again we got the height function, so h of 3 is equal to negative 16 times 3 squared plus 50 times 3 plus 10, and can't do that one in my head, so let's go ahead and figure this out, put this in the calculator. I get 16. Okay. So what does this tell us? Well, after 3 seconds, the velocity of my rock is negative 46. Okay, so real quickly, what does that mean? Okay, I don't remember the last time I drove on the interstate at negative 55 miles per hour, right? Well, when we're talking about physics problems, whenever we go up against the gravity, we have a positive velocity. Well, this is a negative velocity. So what that means is that after 3 seconds, was it a rock or a cannonball? I don't know what we're throwing. But after 3 seconds, it's on its way down. That's what the negative denotes. It means that we are on the way down. So it's falling down at negative 46 feet per second, and it's 16 feet above the ground. And so, you know, here in just a very brief moment, it's going to hit the ground. But that's what that negative velocity means. Again, like I said, you're not traveling. There's no speed limit, negative 55 miles per hour. But when we're talking about physics problems, going up, we have a positive velocity. Going down, we have a negative velocity. All right. So lastly, we have us a pretty tedious word problem. Okay, but it really encapsulates everything that we've done in this section. Of course, that's what you expect from the last example, huh? So looking at the word problem, we have since 2013, the rate of change in the amount of fossil fuel displaced, again, not needed, the fossil fuel displaced, globally became, because of electric vehicles, can be approximated by our function here. Okay. And keep in mind it's d prime of t, so this is our derivative there. So where d prime of t is in thousands of barrels of fossil fuel displaced per year, and t is the number of years since 2013. Okay. So the d, all right, again, the left side of this function would be the thousands of barrels of fossil fuel displaced, and t is just going to be the number of years since 2013. So if we wanted to know, how many barrels were displaced in 2013, we'd put a 0 for t because 2013 is 0 years after 2013, and of course we see we would only displace 7808. But anyways, so in 2016, so keep in mind 2016, that's 3 years after 2013. So in 2016, approximately 24,638,000 barrels of fossil fuel were displaced globally. Okay, so we're given an initial condition here, initial value. Okay, 3 years after 2013, we have this number 24,638. Keep that in mind. So A, find a function d of t, okay, capital D of t, that models the amount of fossil fuel displaced t years since 2013. Okay, well, in order to do this, all we have to do is take d prime of t, right? This is the rate of change, d prime of t, and we just have to integrate it. So let's go ahead and integrate this. Yeah, this is probably going to take up some space here. So let's just go ahead and put our integral sign and just get to work. So we're going to have 1696t cubed right? And then we're going to go ahead and do the thing where we're just going to split this off into um, split each term into an integral of that term. Okay, so we're going to say minus, all right, so put dt, I guess, to be very consistent. So minus the integral of 14,091 t squared dt. We're going to run out of room. Okay, so kind of ran out of room, but not entirely. Trying to get a t there. There we go. Okay, so let's go ahead and integrate each one of these individually. So again, this t cubed turns to a t to the fourth. T to the fourth. Well, let's do it this way. 1696 t to the fourth. Then we're going to divide the entire problem by 4. And for the sake of yeah, let's do it this way, just so I don't erase anything that might be needed. And then we got 14,091 t cubed, and we're going to divide that by my exponent plus 30,420 t squared all over 2, and then minus 7808 t, and then remember, always put plus c. Again, like I said, it's always forgotten, but hopefully we'll remember here. All right, so again, this is going to be d, capital D of t, and let's actually, all right, so let's move this toolbar here, up here. We're going to move the recording up here, and we're going to write this nice and neat because I'm going to snip it and put it on the next page. So capital D of t is going to be, well, what is 1696 divided by 4? It is 424. So 424 t to the fourth minus, hopefully all these are divided nice and neatly. 14, all right, looking good so far. And we can do this one in our head. 15 to 10, so plus 15 to 10. Whew, man, that's a monster of a problem. right, so let's go ahead and, like I said, snip this. We're going to put it on the next page because I'm not in a hurry to memorize all that. Great, missed it. Try it again. All right, so this is our function. Okay, so that's our function, and what information were we given to so we can figure out what c is? Okay, well again, like I said, let's go back. We were told in the problem in 2016, which is again 3 years after 2013, so t is going to be 3, approximately 24,638,000 barrels of fossil fuel are displaced. So I'm going to put a 3 in for t and a 24,638 in for the capital D of t. So it's going to look like 24,638, 24,638. So we're going to write this as 24 t 4 638, and that's equal to, we're going to put a 3 in for all of this, so in for all the t's. Oh man, I hope I can make this fit. All right, so it all fit. Okay, so I'm gonna cheat a little bit and just go ahead and figure out what c is. I'm just gonna snip it in here instead of putting this onto my calculator. It's 3647. So we have c is equal to 3647, 3647. So that means now my function d of t is finally done. We have figured out what c is. So now let's rewrite all this. Plus 3647. All right, so real quickly before I do continue on here, um, I've mentioned in the past, how to write things and you'll make it look nice and easy on the eyeballs. Another kind of pro tip here, and I might have said it before, but I always write my t's like this. I always put a little serif on there and then t. Okay, and the reason why is because of problems like this, where we have t's and addition signs. Okay, and so that way they're more easily distinguished from one another. But anyways, all right, so that was, pretty sure that might have just been the first part. Find a function d of t. Okay, good. So we got our function d of t. Next, we're going to estimate the amount of fossil fuel that will be displaced in 2020. Okay, well, all we have to do here is just simply plug in 7 because 2020 is 7 years after 2013. And I'm going to cheat one more time here. And I'm going to go ahead and put b down here by itself. Okay. And again, all we're doing is just putting 7 in for t, and so we end up with 101,234. All right, and again, that's 1,000 barrels, and 1,000 is a million, so 101 million barrels were displaced. Whew. Okay, so that is our introduction to antiderivatives in this class, and that concludes today's lecture.